Okay, so we're again getting closer to being able to talk about mathematical proofs. There's a little bit that we need to talk about first. So we still need to talk a little bit about quantifiers. One of the things that surprises students the most when we're talking about mathematical proofs is the idea that when you write a mathematical proof, you want to write it using sentences. In fact, the fewer symbols you use, the better. Okay, the less verbose your proof is, the better. You want your proof to be systematic and short, but also accessible to someone that may not know any sort of special symbols. And so there's kind of a balance that you have to strike there. Of course, if you were to write out everything by hand and never use symbols, it would be obnoxiously long and you kind of lose the ability to quickly get your point across. But if you only use special symbols and you don't use a lot of language, then it's going to be hard for people to look at, especially if they're new to understanding the symbols or haven't ever seen them at all. So quantifiers are specific types of symbols that get used sometimes in proofs. I think generally when you write down formal proofs, like for homework or on an exam especially, you'll want to avoid these quantifiers, but they can be very useful for us when we're talking about mathematical ideas, in that they can convey something quickly, very efficiently. So with that being said, these quantifiers should be avoided in formal proofs, but they can still be useful when we're talking about, say, when we're talking about certain mathematical ideas. So there's going to be two quantifiers. There's what's called the Universal Quantifier. And the Universal Quantifier is an upside down capital A, and this means for all or for every. Okay, so this means for all. There's also the Existential Quantifier. Existential Quantifier. And that's a backwards capital E. And that means there exists. Okay, so the upside down capital A means for all. Backwards capital E means there exists. And then this is not really a quantifier, but kind of in the same idea. This implication. So there's two other symbols that sometimes I use. So while not technically a quantifier, it does fall under the symbol category of what I was saying before. Whenever I write that, so if I write an arrow with two lines, that means implies. And if I were to do the same thing, but if it were to have, if it were to be a biconditional arrow, meaning that it has both implications, this means if and only if. When I say that this means implies and if and only if, I mean I'm using these instead of writing down the English words implies or if and only if. So these are just substitutions for English phrases, but they can be useful in quickly conveying something. So for example, our example before, that if X is odd, then Y, so if, what did we say before? If X is odd, then X plus 1 is even. We could write as, so if I wanted to do this the old way, we would say if X is odd, then X plus 1 is even. Or I could say X is odd implies X plus 1 is even. Okay, so that's kind of the context. It saves a little bit of time. That's kind of the context where these will be used. This second version is not a great phrase for a proof because it kind of presupposes that you know what that symbol means, and maybe we don't, or maybe, yeah, I mean, sometimes it's just not appropriate to use a symbol. Sometimes the meaning is much more clear to more people if you just use English. So those are two quantifiers and then two additional symbols. And then what we're going to get into is we're going to talk about nested quantifiers. So really what's going to happen is we're going to want to take our quantifiers, the for all and the there exists, and we're going to want to put them together. We're going to want to put them in some order together. And so, for example, I think this will just be easiest if we talk about some example. Let's say that we want to determine the truth value. Let's say our domain is all real numbers. And we want to determine the truth value of the following. We want to know, does there exist an x, does there exist a y, such that x plus y equals 5. We're allowing x and y to be real numbers. So when I say that that's their domain, that's what I mean is that we're allowing x and y to be real numbers. And this is not the same as the domain of a function. Just, I mean, x and y are allowed to be reals. And so is this statement true or false? Does there exist an x and does there exist a y such that x plus y equals 5? And I think you'd agree that the statement is true. Okay, because for example, you can take, so one way that you can prove a there exists statement is you can actually come up with an actual explicit example. So you could take, for example, x equals 2 and y equals 3. There's infinitely many examples that you can pick. But this is a true statement. What about the statement for all x and for all y? X plus y is 5. This, of course, is false because this is not true if, say, x is 1 and y is 1. Okay. This example where the statement fails. Okay, so I think that this is worth pointing out. To show that a there exists statement is true, you need one example. To show that a for all statement is false, you also need one example. This is called a counterexample. Okay, so this is called a counterexample. This is just an example that shows that your for all statement is false. Okay, and so those are going to be very useful for us. Now, what's a little bit trickier is if you want to say for all x and for all y, x squared plus y squared is greater than or equal to 0. Okay, so we want to know, if we want to prove that this statement is true, and of course it is true, we can't just come up with an example. Okay, no example will do it because we're saying that this is some statement for all x and y values. You can't do this by example. There's uncountably many real numbers. Okay, so there's no way that you can list them. The fact that there's even infinitely many is problem enough. So we have to do something else. We have to somehow sort of justify that this statement is true. And so we'll talk about exactly how we do that as we go along. In this case, this is easy enough to justify by showing that for real numbers, x squared is greater than or equal to 0. And we could do that by cases, saying considering whether x is positive or negative or 0. And likewise for y squared being greater than or equal to 0, depending on whether y is positive or negative or 0. And then if you add two numbers that are at least 0, then that sum is also at least 0. So there's some steps that you could take. I'm not going to formally write that down, but somehow your justification can't just be examples. So you have to be very careful about that. So to prove a for all statement is true, you have to give some sort of justification. You have to give some sort of a logical, thorough reason. Okay, so that's essentially what a proof is it's a sort of formal justification that a statement is true. It's not always the case that you can do this with examples. In fact, in most cases, you can't just prove something by examples. You have to justify it somehow. Now, let's think about another statement. Let's say I want to prove that there exists an x and there exists a y such that x squared plus y squared equals -2. Okay. How could we prove, so this of course is false. There are no real numbers, x and y. Notice that if I change the domain, the statement could be true. If I allow complex numbers, then I could let x and y both be I, so that I squared is -1. Add them up, you get -2, everything's fine. But this statement is false if our domain is all real numbers. So we somehow again have to justify that this is false, because what we're saying is that no matter what your x and y values are, this is not going to happen. Okay, so to prove that that is false, to prove that their exist statement is false, you have to, again, justify it rigorously using a mathematical proof. There's no amount of examples that you can talk about generally that'll prove that this is false. Okay. Now, one of the things that we just hinted at, and one of the things that'll be useful, is negating quantifiers. So let's just work in the abstract, and let's say P of X is some proposition like X is greater than or equal to 2. And you want to know what does it mean to negate that proposition. Again, when you put too many symbols together, even this looks a little bit silly. So that's why we don't like to use symbols unnecessarily. It kind of buries the meaning a little bit. It makes it a little bit less clear what's actually going on, which is bad. So, but in general, if you want to negate a for all statement, think about what it means to show that for all x, P of X is false. And I forgot the X, how dare me. If you want, you can put that in parentheses, but those aren't really necessary. So if I want to negate the statement that for all x, P of X, in other words, I think another way to think about this is you want to prove that for all x, P of X is false. That's really what it means to negate it. That's equivalent to saying that there exists some x such that P of X is false. In order for the for all statement to be false itself, that means that there must exist a value where P of X fails. In other words, there exists an x such that not P of X. Okay, so this is how we're going to negate for all statements. And this goes the other way as well. If you want to show that a there exists statement is false, so think about the statement that there exists an x such that P of X. In order for that to be false, what needs to happen is that for all x, P of X has to be false. Okay, so this is how we negate. I think this is useful just to keep in mind. This is how we negate for all and there exist statements. Okay, and I think that also helps us make sense of why these work the way they do, right? Why is it that if you want to prove a there exists statement true, that's the same as proving a for all statement false, right? So that's really what we're getting at here.